So this is a special session to commemorate the loss of two of the great Indian mathematicians, Seshadri and Narasimhan. They made a great impact on all of mathematics and physics, and especially on the subject matter of this course. So Edward Witten is going to be our next speaker, and he's going to talk about the work. Edward, please.
Thanks, Ron, and thanks for the invitation for this talk. So it was an honor to be invited to lecture at this special event in memory of Narasimhan and Seshadri. But at first I wasn't sure if I should accept, because I felt my point of view would be somewhat limited. So I can explain their work sort of from the point of view of a physicist, making use of some of the results afterwards. But I'm not really able to fully explain what they did from their point of view when they were doing it. But I decided I could give a perspective on how parts of their work have influenced physics, including my own work. So in the beginning of this talk, I'll start with a short overview of what the topics will be, and then we'll go over some of the topics in a little more detail. So in 1964, Narasimhan and Seshadri proved a fundamental theorem about the relationship between unitary representations of the fundamental group of a Riemann surface and homomorphic vector bundles over the surface. I'm pretty sure that neither they nor anyone at the time anticipated any connection to physics. The beginning of the connection came in '82, when Atiyah and Bott put the Narasimhan-Seshadri theorem in the context of gauge theory, which is relatively far away from the way they were looking at it when they proved the theorem. By this time, Seshadri had made several important extensions of the original theorem, which I'll tell you about later. One extension was a technical sounding one to include semi-stable bundles, not just stable ones. It's a technical sounding extension, but it's extremely important for later developments. And the other involves what are called vector bundles with parabolic structure, which at first might sound like a somewhat exotic generalization, but it's also very important for applications. When Atiyah and Bott were rethinking Narasimhan and Seshadri in the context of gauge theory, important background came from another result of Narasimhan, this time with Harder, and this had to do with the cohomology of the moduli space of homomorphic bundles on a curve. And I'll say a word about that also. So actually, well, one reason that Seshadri's extension with semi-stable bundles was important. Well, okay. It's important to have a compact moduli space here. In 1983, Donaldson, inspired in part by Atiyah and Bott, gave a new proof of the Narasimhan-Seshadri theorem from the standpoint of gauge theory, and that later had many generalizations. The generalization that's most directly related to this course or program we're having on geometric Langlands was by Hitchin. He introduced Higgs bundles, and he showed that a correspondence between complex flat bundles and Higgs bundles. And that correspondence actually is the analog of the Narasimhan-Seshadri theorem. I wrote for Higgs bundles, but I could have equally well written for non-unitary flat bundles. So Hitchin's result extends Narasimhan-Seshadri to Higgs bundles rather than bundles, and non-unitary flat connections rather than unitary ones. Now, of course, Hitchin's work is very important for understanding geometric Langlands via gauge theory, so it figures in various lectures in this school. Also in the 1980s, the Narasimhan-Seshadri theorem was generalized to complex manifolds of higher dimension. It's often called the Kobayashi-Hitchin correspondence. Different versions were proved by Donaldson and by Uhlenbeck and Yau, and later there were many generalizations. Now, these things at their inception sounded very far away from physics, but by the mid-80s, physicists were using homomorphic vector bundles on Calabi-Yau manifolds to make models of particle physics from string theory. And then the theorems I've just mentioned, which establish an equivalence between homomorphic bundles and something more differential geometric, were very important in the applications for physics. So this is what originally caused a larger number of physicists to be familiar with some of the things I've mentioned. But the time the Narasimhan-Seshadri theorem was most important for me started in 1988, when I was trying to understand the quantization of Chern-Simons gauge theory in 2+1 dimensions. So I'll go back to that story later. Finally, even in this mini overview, there are a couple other things I should mention. So one is that, well, Narasimhan wrote a series of papers on homomorphic bundles on Riemann surfaces, but in particular, Narasimhan and Ramanan introduced geometric analogs of the Hecke transformations of number theory. And these were very important in geometric Langlands, and their physical interpretation in terms of 't Hooft operators is actually something I described the other day, I think on Friday. So finally, in one of his later papers, Seshadri with Balaji made yet another important generalization of the notion of a vector bundle on a Riemann surface. This involved parahoric structure, which is more general than the parabolic structure that Seshadri had developed in the 70s. And I will say a few words about this, but Balaji is one of the speakers in today's program, so he may say much more. So now that's sort of the table of contents for this talk. And now I'll go over some of the topics in more detail. So first of all, the Narasimhan-Seshadri theorem compares flat bundles and homomorphic bundles on a Riemann surface sigma. Any flat bundle has a natural homomorphic structure. I think Narasimhan and Seshadri would have explained it as follows. So let sigma be a Riemann surface and let H be its universal cover. For instance, if sigma has genus bigger than 1, then H is the complex upper half plane. Then consider a rank n trivial complex bundle over H, just the product H times Cn. So as a trivial bundle, this is a flat bundle and also a homomorphic bundle. Now, any flat bundle over sigma as opposed to H is the quotient of this trivial flat bundle over H by an action of the fundamental group of sigma, where the fundamental group of sigma acts in a natural way on the universal cover H. And to make it act on Cn, we pick a homomorphism from the fundamental group of sigma to GLN. So the quotient E, which is H times Cn divided by pi 1 of sigma, it's a vector bundle over sigma. And it's flat because we just divided by a discrete group. But it comes with an obvious homomorphic structure. A local section S is homomorphic downstairs, that means over sigma, if it pulls back or if it comes from a homomorphic section upstairs over H. Now, Etienne Bott, taught gauge theorists to state this a little bit differently. So from a gauge theory point of view, you'd say the following. A flat bundle E is a bundle with a flat connection A. And that means it has a gauge covariant exterior derivative d sub A, which is the ordinary covariant derivative plus the action of A. Now, d sub A has a 0, 1 part and a 1, 0 part. Forgetting the 1, 0 part and just keeping the 0, 1 part, the 0, 1 part d bar A defines a homomorphic structure of E. So here it's important that there's no integrability condition for a d bar operator in complex dimension 1. In complex dimension 2 or higher, things would not be as simple as this. So just by forgetting the 1, 0 part of the connection and keeping the 0, 1 part, we define a homomorphic structure for every flat bundle. So in the rank 1 case, in other words, this sigma is a Riemann surface and curly L is a homomorphic line bundle. A classical result says that L admits a unitary flat connection if and only if L has degree 0, or equivalently if its first Chern class is 0. So Narasimhan and Seshadri became interested in the analogous question for a homomorphic vector bundle E over sigma of rank n bigger than 1. Does E admit a unitary flat connection, which in this case would have structure group UN? Well, there's an obvious necessary condition, again, that C1 of E should be 0. Otherwise, because C1 of E would determine the integral of the trace of the curvature. So if it's not 0, the curvature of a connection can't vanish. But that's far from the whole story. To see why, there are further constraints. Let E be the rank 2 bundle O of P plus O of minus P, where P is a point in sigma. O of P is the line bundle that's trivial away from P, but a section is allowed to have a simple pole at P. O of minus P means you require a 0 at P. So this this vector bundle E has first term class 0 because the first term class cancels between the two pieces, but there's no unitary flat connection. A short proof is as follows. First of all, O of P has a holomorphic section that vanishes at P. And that gives a holomorphic section of E that vanishes at P. 0 in this component. And in this component, the section that's 1 away from P and has a 0 at P. But if E has a flat unitary connection A, and if S is a holomorphic section, then by integration by parts, after picking a Kähler metric on sigma, you can prove this identity, where I use the fact that the connection is flat. We have to integrate by parts in comparing these two, and we'll get a term proportional to the curvature of the bundle. But in the case of a flat bundle, that vanishes. And so we get this formula, but by hypothesis, d bar of S is 0, so the right-hand side is 0. And therefore, the left-hand side is 0, proving us that the DAS is 0. In other words, S is covariantly constant. But if it's covariantly constant, assuming it's not identically 0, it can't have any zeros. So that argument shows that this is an example of a flat bundle with first term class 0 that has no unitary flat connection. I don't think this explanation is too close to what Narasimhan and Seshadri would have said in 1964. This is a gauge theory explanation in hindsight. Now, Mumford had defined the notion of a stable holomorphic bundle over a Riemann surface. So for simplicity, I'll define it just for bundles with first term class 0. A bundle with first term class 0 is unstable if it has a holomorphic subbundle E prime of positive degree. For example, the bundle we just looked at is unstable because it has a subbundle O of P of positive degree. Mumford also defined E to be semi-stable if it has a proper subbundle E prime of degree 0, but none of positive degree. If every proper subbundle has negative degree, then E is said to be stable. So the original version of the Narasimhan-Seshadri theorem said that irreducible unitary flat bundles of rank n are in one-to-one correspondence with stable bundles. The easier direction is to show that for a holomorphic bundle to have a flat unitary structure, it has to be stable. In other words, the easier direction is to show that stability is necessary for flatness. That can be proved by generalizing the argument I gave for O of P plus O of minus P, although this is probably not too close to how Narasimhan and Seshadri expressed the argument. But still, in their discussion, that was the easy direction. The opposite direction is more difficult. Stability is sufficient for existence of a flat unitary structure. I don't think I can usefully explain the proof, and chances are some of you on this at this meeting can explain it much better than I can, so I won't try to explain how they proved it. I've stated this for bundles of degree 0, but they actually had a more general statement about bundles of rank n and degree d for any d. In gauge theory language, the statement is that instead of flat unitary bundles, you talk about unitary bundles whose curvature is central. In other words, the curvature is a multiple of the identity. The integral of the central curvature is then the first term class. So it's this degree d, this integer d, times 2 pi. Narasimhan and Seshadri weren't working with gauge theory, so their formulation was different. And the moduli space they constructed is smooth and compact if and only if n and d are relatively prime, which I'll write like this. So n comma d is the greatest common divisor. If that's 1, then the moduli space of stable bundles, which is restating the result in terms of gauge theory, it's the moduli space of flat unitary bundles with central curvature. It's smooth and compact in the co-prime case, not otherwise. So Seshadri, as I explained in my overview at the beginning, went on to extend the theorem in two directions. So one involved this non-co-prime case. In the co-prime case, stable bundles give a smooth, compact moduli space. But the moduli space of irreducible unitary flat bundles isn't compact if D and N are relatively prime. For example, in the most basic case that D is 0, which we started with, the moduli space isn't irreducible. In the D-brane era, physicists understood this as follows. D and N are two D-brane charges. You're looking at D-branes wrapping on a Riemann surface. So let's say N is a 2-brane charge and D is a 0-brane charge. If D and N have a common factor, then you can separate the D-branes into two clumps, which have the same ratio of D and N, so they can be mutually BPS, and you can make that separation in a supersymmetric fashion. If D and N are relatively prime, there's no way to supersymmetrically separate your D-brane clump into two clumps. And the gauge theory statement is that the moduli space is compact and smooth. So the first extension I'll describe by Seshadri is for the case that, well, in D-brane language, you could separate the system into two subsystems. And in that case, the moduli space of stable bundles isn't compact, and Seshadri wanted to find a nice compactification. So he extended the Narasimhan-Seshadri theorem to an equivalence between compact moduli spaces. On the one side, the moduli space of unitary flat bundles that are not necessarily irreducible, and the moduli space of homomorphic bundles that are stable and or semi-stable. So in other words, on one side, he allowed the unitary bundle to be reducible. On the other side, he included semi-stable bundles. So the moduli space of homomorphic bundles that are stable and or semi-stable is usually called for short the moduli space of semi-stable bundles. But semi-stable is allowed to include stable in that terminology. Now, the key subtlety that Seshadri had to accomplish was to understand and incorporate an equivalence relation for semi-stable bundles. You might think from the name that the moduli space of semi-stable bundles parameterizes all semi-stable bundles, but in fact that wouldn't work. There isn't a sensible Hausdorff moduli space that would parameterize all equivalence classes of semi-stable bundles. So I'll explain this in gauge theory language, which again isn't precisely the way Seshadri would have said it. Consider a rank 2 bundle E that's a direct sum of line bundles of degree 0. Such an E is generically semi-stable. If L has non-zero degree, E would be unstable, because then either L or L inverse has positive degree, and having a positive degree subbundle would make E unstable. But so we consider the case that L is of degree 0. Now, such an L has a C-star group of automorphisms, where you act as lambda on L and as lambda inverse on L inverse. Now, the direct sum has a D-bar operator that looks like this. Ordinary D-bar plus a diagonal gauge field. Let's make an upper triangular perturbation for sum C. In general, such a deformation exists. When I say the deformation exists, I mean that C can't be gauged away. So we're interested in the case of an upper triangular perturbation that's essential, meaning it's not a pure gauge. However, we do have the C star symmetry, and by the action of C star, we can replace this with this, where I can rescale C as I wish by a suitable element of C star, which actually should be lambda to the 1/2 up here. So the bundle E prime lambda defined by the D-bar operator on the right-hand side has a holomorphic type that's independent of lambda as long as lambda isn't 0. On the other hand, as lambda equals 0, E prime reduces to E, and its holomorphic type is different. So if we include the bundle with non-zero lambda, Since lambda is arbitrarily small, that bundle should be considered it can be reached from E by an arbitrarily small perturbation. So this would be a non-Hausdorff space. This bundle would be contained in any, if you had a moduli space that included parameterized arbitrary semi-stable bundles, then E prime would be in any neighborhood of E. Or differently put, E is in the closure of E prime. So E prime would represent a point in the moduli space that wouldn't be closed. So if you're going to get a sensible moduli space of semi-stable bundles, you have to treat E and E prime as equivalents. So Seshadri, to construct the moduli space, needed the equivalence relation of S equivalence, as he called it, I think, in which basically you consider any triangular deformation to be equivalent to the direct sum. And then he constructed a compact moduli space of equivalence classes of semi-stable bundles and proved it's equivalent to the moduli space of unitary flat bundles, not necessarily irreducible. So that statement of the result is for degree 0. There's some more general statements for other degrees. Now, apart from the fact that the result itself was important, the ideas were also important in many later constructions of moduli spaces in algebraic geometry. So now I come to Seshadri's second generalization of the theorem. Well, in terms of unitary bundles, he considered flat unitary bundles on a surface with punctures. So there's genus 0 surface with 5 punctures. On one side of the correspondence, he considers flat bundles with prescribed conjugacy classes of the monodromy around the punctures. On the other side, he considers homomorphic bundles with parabolic structure, where parabolic structure is defined to be a reduction of the structural group of a bundle at a puncture from GLNZ to a parabolic subgroup, which is roughly a group of block upper triangular matrices. So in a special case, parabolic structure would mean a reduction to a group of, well, when I say upper triangular, you're allowed to have non-zero elements on the diagonal. So upper triangular in that sense. So here you have to generalize ideas of stability, semi-stability, and S equivalence to parabolic bundles. And the story is more complicated than the previous case because the stability condition depends on some parameters. It has to because on the unitary side, we specified the conjugacy class of the monodromy around the punctures. But that involves some continuous parameters. For example, for SU2, the conjugacy class is a rotation angle, but it's a continuous angle from 0 to 2 pi. So somehow in the algebra geometric side, and that's a real parameter. So usually in algebraic geometry parameters are complex. So you might be puzzled about how to incorporate the real parameters of the monodromy in terms of algebraic geometry. So in Seshadri's story, you have to generalize stability to parabolic bundles. The generalization isn't unique, but involves some free parameters. And those parameters correspond to the conjugacy class of the monodromy in the other description. So I think it's a surprising answer for what is the algebra geometric analog of the monodromy. After finding the right definitions, Seshadri proved a correspondence between flat bundles with prescribed monodromy and semi-stable parabolic bundles, flat unitary bundles with prescribed monodromy. And later we'll mention 2 applications. One to geometric Langlands and one to Chern-Simons gauge theory. Now, I'm also going to mention 2 contributions by Narasimhan from the same period. First, with Ramification, he introduced a geometric analog of the Hecke transformations of number theory. So in number theory, roughly speaking, the Hecke operator is a change that only acts at 1 prime. So the geometric analog of Hecke transformation is a modification of the homomorphic structure of a homomorphic bundle at just 1 point in a Riemann surface. So it would be impossible to modify the structure of a flat bundle at 1 point. If you're given a flat bundle away from some punctures, what happens if the punctures is uniquely determined. But holomorphically, you can modify a bundle just at one point. For example, for a line bundle, the trivial line bundle O and the line bundle O of P, where you're allowed to have a pole at P, are the same except at one point. That's for an abelian group. They generalized this to a non-abelian group and introduced modifications of a holomorphic bundle at just one point. So transformations played a central role in the geometric Langlands program developed around 1990 by Valens and Indranil and then many others. And on Friday, I explained the gauge theory interpretation of geometric Hecke transformations in terms of 't Hooft operators. What I actually didn't do on Friday was to explain in detail the algebra geometric definition. What I did was to just show that an 't Hooft operator would produce a change in the holomorphic structure of a holomorphic bundle at just one point. Also in the 70s, Narasimhan and Harder computed the Betty numbers of the moduli space of stable bundles in the case n comma d equals 1, where this is smooth and compact. By the way, in the smooth compact case, the bundles are all stable, so I called it the moduli space of stable bundles, not semi-stable ones. They did this in a very surprising way, miles away from gauge theory, by comparing to characteristic P and using the Weil conjectures, which were proved by Deline at just about this time. They introduced, they considered not just stable bundles, but all bundles over a curve. And here a curve means a curve of character, well, what's said in this sentence doesn't depend on characteristic P. So if you have a holomorphic bundle over a curve that is a Riemann surface in the complex case, it might be stable or it might be unstable. They stratified it by how unstable it is. Roughly, for semi-stable bundles, I explained that I explained an example that a semi-stable bundle is in an equivalence class with a semi-stable bundle that's a direct sum. So they introduced a stratification where the strata are labeled by direct sums, roughly, and a possibly unstable bundle that might not be a direct sum still is labeled by a direct sum that in some sense it's related to. Anyway, after stratifying the space of all bundles, in the case of a curve over a finite field of characteristic P, they wanted to count the stable bundles, but they did that as follows. The unstable bundles are relatively easy to count because they are related to direct sums, and the direct sum has lower rank. So by induction on the rank of a bundle, they had a good way to count unstable bundles. And then they had a sum rule that told them how to count stable bundles once they knew how to count unstable bundles. And the form of the answer was such that with the help of the Weil conjectures, it determined the Betty numbers of the moduli space of stable bundles. So all that, see, when I say Betty numbers, it sounds like ordinary topology of a complex manifold, the moduli space of stable bundles. Here they computed the Betty numbers in characteristic P. Now, a number of years later, Etienne Bott introduced a gauge theory perspective on the Narasimhan-Seshadri theorem and also the Narasimhan-Harder story about the topology of the moduli space of stable bundles. So Etienne Bott considered gauge theory of a compact group G on a Riemann surface sigma. I'll call the gauge field A and the curvature F. This should be uppercase A here. The Yang-Mills action is the usual one. Their basic idea was to consider the action as a Morse function, or more precisely an equivariant Morse function on the space of all connections. So equivariant means you take account of symmetry, and the symmetry they took account of was gauge equivalence. In Morse theory, you have to consider the critical points. A critical point here, it just means a point where the action is stationary. In other words, a solution of the Euler-Lagrange equations. So they looked at all the solutions of the Euler-Lagrange equations of Yang-Mills theory in 2 dimensions. The ones that minimize the action are the flat connections with action 0. These flat connections are automatically unitary because the gauge group G was assumed to be compact. So the holonomy of the gauge group, gauge field, there'll be elements of the compact group G. Now, according to Narasimhan and Seshadri, the critical points at I equals 0 correspond to stable homomorphic bundles. Ati and Bott showed that the other components of critical points are in one-to-one correspondence with the strata of the Narasimhan-Harder stratification. So, as some of you will know from having thought about two-dimensional Yang-Mills theory, the Euler-Lagrange coefficients are easy to solve because they show that F is covariantly constant. And then from the center of the, then F, if F isn't identically 0, it's a non-zero element of the Lie algebra, and it at least commutes with itself. So there's an unbroken abelian subgroup, and the curvature in that unbroken abelian subgroup, well, it's in one-to-one correspondence with the Narasimhan-Harder strata. Now, it turns out that the Morse indices of critical point sets are all even. And so Ati and Bott observed that if Morse theory applies to this situation, as they conjectured, then the Yang-Mills action is an equivariantly perfect Morse function on the space of all connections, where the equivariance is with respect to the gauge group. And they showed that this would imply formulas for the Betty numbers of the moduli space of stable bundles that agree with those of Narasimhan and Harder. Here they use the fact that the space of all connections, where you ignore here the action of the gauge group, is contractible. That's because you can take convex linear combinations of connections. If A0 and A1 are connections, and so is T A0 plus 1 minus T times A1. So using that, you can prove easily that the space of connections is contractible, and that played for them a role analogous to Tamagawa number equals 1 for Narasimhan and Harder. Now, years later, it was proved that Ati and Bott's conjecture is correct, and Morse theory does apply in this problem. So if one knows that, that implies the formulas for the Betty numbers. Not knowing that, Ati and Bott avoided analytical difficulties by instead considering the action on the space of connections of the complexification of the gauge group. I won't go into this today because it would take us away from our main subject of the work of Narasimhan and Seshadri. But anyway, there were further important ideas in the way that they can, sorry, in the way they completed the proof. There were further important ideas. Maybe I'll stop here for questions.
There's nothing in the chat.
Okay. So the only thing I'll add here then is that near the beginning of my lecture, when I was explaining some facts relevant to the theorem, I used gauge theory language that was introduced for this problem by Ati and Bott.
A question just did show up in the chat if you'd like to take it.
Sure.
So in using Narasimhan and Seshadri's theorem, instead of basing it on Morse theory, Ati and Bott's paper, is it true that if dealing with complex manifolds, one can base it on the so-called Picard-Lefschetz theory?
It's true you can adapt Picard-Lefschetz to gauge theory, but well, one reason it's hard for me to answer is that I think of Picard, I would use Morse theory in trying to apply Picard-Lefschetz theory. I don't think I can give a useful answer on the fly.
Okay, please go on.
Okay. So the Ati and Bott paper inspired a new proof of the Narasimhan-Seshadri theorem by Donaldson, placing it in the context of gauge theory in 1983, which was the year after the Ati and Bott paper. And then there were many generalizations after that. The one that's of particular importance in this program that we're having now is due to Hitchin. Narasimhan and Seshadri had interpreted unitary representations of the fundamental group of a Riemann surface in terms of algebraic geometry. But what about representations that aren't unitary? Well, Hitchin answered that question. He proved that semi-stable and not necessarily unitary I haven't told, okay, if you want to consider non-unitary representations, then you do need a stability condition. So previously I mentioned that Seshadri had needed, well, Narasimhan and Seshadri had needed a notion of stability for homomorphic bundles, even in their original theorem. Unitary flat bundles can be considered automatically stable. For non-unitary ones, you need a stability condition, which roughly again says that you consider an upper triangular flat bundle to be equivalent to its diagonal cousin. Hitchin proved that semi-stable and not necessarily unitary representations of the fundamental group of a surface correspond to semi-stable, I should have written Higgs bundles, E phi, where E is a homomorphic bundle and phi is a homomorphic map from E to E tensor K, which Hitchin called a Higgs field by a very rough analogy with the Higgs field of particle physics. So extending this, Hitchin proved that the moduli space of either of these two types of objects has a hyperkähler structure. It's a complete hyperkähler metric. And those are important facts as input to other lectures at this school. So this was the generalization of Narasimhan Seshadri for non-unitary flat bundles. Also in the 1980s, using the gauge theory formulation, Narasimhan Seshadri was generalized to complex dimension manifolds of dimension greater than 1 by Donaldson and by Uhlenbeck and Yale. In higher dimensions, the theorem says that a semi-stable homomorphic bundle admits a Hermitian metric such that the corresponding connection satisfies the Yang-Mills equations. It's called a Kähler-Yang-Mills connection, or sometimes. Conversely, a homomorphic bundle with such a Hermitian metric is semi-stable. Now, when I was first hearing about these things from Atiyah and Bott in the early 80s, they seemed ridiculously far away from physics and completely unimaginable that anybody could think of such things. But, well, two things happened. One is that Atiyah and Bott taught us that stability and semi-stability had a meaning in terms of symplectic geometry, where you're taking symplectic quotients rather than trying to take a homomorphic quotient. But of even greater impact, physicists became familiar with such matters in the mid-80s because Calabi-Yau threefolds and homomorphic bundles over them were important for making models of particle physics. So in this context, the existence of Hermitian Yang-Mills metrics is completely crucial. It's the starting point for studying a model in string theory, and this has become an important direction. So in this context, when you look at the low energy effective action in space-time of the particle physics model, the notions of stability and semi-stability suddenly make sense as a particle physicist, because you can see the conditions coming in as conditions in the low energy effective action. So if you're a physicist, these rather mysterious definitions of semi-stability and so on were perhaps demystified in the mid-80s when it was used in particle physics. But instead of talking about that, I'm going to explain the role of the Narasimhan-Seshadri theorem in my own work a few years later on rational conformal field theory and the Jones polynomial. But it would be a little, well, first of all, some of you might know the story. I suspect that many of you know that the Jones polynomial is related to Chern-Simons gauge theory, but might not be familiar with the role of the Narasimhan-Seshadri theorem there. It's because of that last thought that I decided to explain this. But it's hard to properly explain the role of the theorem without putting it in context. So I'm going to have to spend a few minutes as background on the Jones polynomial. So Vaughan Jones discovered the Jones polynomial of a knot in 1983. This is just a knot in ordinary three-dimensional space, R3 if you like. It's a subtle invariant that from the beginning had many relations to mathematical physics. Even in Jones's original work, Jones's original definition involved the Jones representations of the braid group, which by the time I think the original paper was published, he knew were related to the temporally-Lieb algebras of statistical mechanics. So from the beginning, there were relations to mathematical physics. So since he used the braid group, let me take a moment to explain that. A braid in the mathematical sense is a picture like this. Time runs vertically, the two-manifold space runs horizontally. Points move around in the plane as time evolves. If you want a closed braid, you could have to make the initial, well, sorry. A braid by definition is a configuration of points that start and end at the same points on the plane. So we let the particles end at their starting positions, collectively, not individually. Here I've drawn a braid where most of the particles don't end at their starting positions, but well, the intent of the drawing is that the four final points are the same as the four initial points. So that's a braid in the mathematical sense. It's a braid with four strands. Now braids form a group because they can be decomposed by gluing one braid on top of another. If I have a braid and another braid, because the ending points and the starting points are the same, I can just literally glue them together end to end. And it's fairly obvious that topological classes of braids form a group. So Jones's original definition of the Jones polynomial was as follows. First, we can build a knot by gluing together the top and bottom ends of a braid. I haven't drawn a picture, but in your mind's eye, just imagine gluing this here, this one here, and so on, without letting them cross. So we glue the top strands to the bottom strands in a way that doesn't introduce any more topological complications. Gluing is a bit like taking a trace. So Jones considered traces of braid group representations. Let B be a braid and let R be a representation of the braid group. And let's write curly R of B for the matrix that labels this braid B and this representation R. I see in this sentence I jumped ahead of myself a bit. In his original work, Jones constructed representations Ri of Q that depend on a complex parameter Q, and for each Q there was a finite set of representations. And then, well, a finite set if you have a fixed number of strands. So for 4 strands, Jones had 2 representations for each Q. And then he constructed then he defined the Jones polynomial as a linear combination of the corresponding traces. So you take the trace of the representation matrix in the representation Ri of Q, and you sum it over I with some coefficient Ci of Q. It worked in the sense that it gave a knot invariance, but it was unclear why, because there was no manifest 3-dimensional symmetry in the construction. A braid has a preferred time direction, so there's no 3-dimensional symmetry, there is 2-dimensional diffeomorphism symmetry. You're even allowed to make time-dependent 2-dimensional diffeomorphisms, but there's no true 3-dimensional symmetry for braids. And why you'd get 3-dimensional symmetry if you take these particular braid group representations and these particular coefficients and add them up was not clear. Michael Atiyah recommended this problem for physicists. A very important step was taken by Tsuchiya and Kanya. They showed that the Jones representations of the braid group are the ones that arise when you decompose the correlation functions of the 2-dimensional WZW model in conformal blocks, as originally analyzed by Knizhnik and Zamolodchikov. So, for example, well, for illustration, it's illustration, but it's also the case that Knizhnik and Zamolodchikov analyze in detail. Consider G0 correlation functions of a primary field phi. Well, they're functions of the positions of points on the Riemann surface. They're neither holomorphic nor anti-holomorphic, and they can't be factored as the product of a holomorphic and an anti-holomorphic function. But Knizhnik and Zamolodchikov had showed that these functions are finite sums of products of holomorphic and anti-holomorphic functions. So the F alpha are multi-valued holomorphic functions. Since they're multi-valued, they have monodromies, and that gives representations of the braid group. So for each n is the number of points, you can define a vector bundle over the configuration space of n distinct points with a basis given by the F alpha. These are automatically flat vector bundles with the F alpha understood as covariantly constant sections. And their monodromies when the points move around give representations of the braid group. The representations are actually unitary, as follows from the fact that these correlation functions are single valued. Well, and other properties of the W0 model. The flat bundles must be unitary. Tuccia and Kania showed that for the gauge group SU2 and a primary field in the two-dimensional representation, the flat bundles you get this way are the Jones representations of the braid group. The functions f alpha that appear in this decomposition are called conformal blocks. Eric Verlinde defined operators that act on the space of conformal blocks. And intuitively, it seemed he was treating the space of conformal blocks of the WCW model as the Hilbert space of some quantum system. I can't remember now how explicit he was in stating this, but what he was saying suggested that kind of intuition. But what was the system whose Hilbert space is the space of conformal blocks of the WCW model? At some point, I had the idea that the appropriate quantum system was simply Chern-Simons gauge theory, with the action being the Chern-Simons function, where A is a connection on a G bundle over a 3-manifold W, and K is the level of the WCW model. G is supposed to be the same group used in the WCW model, and K is the same level. Because this action, unlike the Yang-Mills action, is defined only using an orientation of W and no metric, you can hope that whatever you get from it will be topological and will give 3-manifold invariance. You can include a knot or embedded circle K by including a Wilson operator, which is just the trace of the holonomy around the knot. This is the way physicists write the holonomy in the representation R. And now the path integral with an insertion of the holonomy depends on the knot and the representation and also W, but nothing else. So you might hope, taking W equals R3, that this will give an invariant of a knot. It turns out these statements need slight modification. Because of an anomaly, both the 3-manifold and the knot have to be framed, which means the tangent bundle of W and the normal bundle of K need to be trivialized, need a homotopy class of trivializations. So this was the idea, but to get anywhere with it, you need to know that the quantum Hilbert space H sigma of Chern-Simons theory on a Riemann surface sigma is the same as the space of conformal blocks of the WCW model on sigma, with the same symmetry group G and the same level K. Well, why would this be true? That's where the Narasimhan-Seshadri theorem comes in. First of all, to construct the quantum Hilbert space, we're supposed to quantize the classical phase space, which, as we discussed Thursday, is a troublesome operation generically. The Euler-Lagrange equations of the Chern-Simons action just say that F, the curvature, should vanish. So the phase space we have to quantize to construct the Hilbert space is the moduli space M of flat connections on a 3-manifold R times sigma, where sigma is space and R parameterized as time. And because R times sigma is contractible to sigma, it's the same as the moduli space of homomorphisms, rho, from pi 1 of sigma to G, the compact gauge group. Somehow, we have to quantize M and show that the result is the same as the space of unitary blocks of the WCW model. M should be quantized with symplectic structure K times omega naught, or omega naught over 2 pi generates the integral, well, it's a Durham cohomology class that comes from an integer cohomology class. The condition ensures that a pre-quantum line bundle exists, so that quantization is possible. So anyway, we have to quantize this moduli space of flat bundles with a certain symplectic structure. That's K times a fundamental symplectic structure. Now, as we discussed Thursday, there's no known way to quantize M, and presumably there's no way to quantize M without picking some additional structure. Suppose we choose the additional structure to be a complex structure on sigma. Then we can invoke the Narasimhan-Seshadri theorem. It says that M is the same as the space of the moduli space of semi-stable homomorphic G bundles over sigma. Knowing this, we can quantize M using geometric quantization. There's a fundamental line bundle L over M, whose first Chern class is represented in Durand cohomology by omega naught. This thing I didn't define very clearly, perhaps, as the fundamental quantizable symplectic form. If the gauge group is SUN, L is the determinate line bundle of the Dirac operator on sigma, coupled to a rank n homomorphic vector bundle over sigma. For other groups, there isn't quite as nice a definition of L in algebraic geometry. In differential geometry, you can. Then L to the K is a pre-quantum line bundle for this problem in the language of geometric quantization. And geometric quantization tells us we should define H naught of M with values in L to the K as a quantization of M. At this point, we get lucky. The answer, H naught of M with values in L to the K, coincides with an already known and, in a sense, standard, although rather abstract, description of the space of WZW model conformal blocks on a genus G surface. Although my memory is fuzzy, I believe I learned this description from Graham Siegel, and I was lucky because the description was certainly not well known among physicists at the time, possibly also not today. It's widely used in a more general form by mathematicians working on geometric Langlands. So that was the basic link between 2 and 3 dimensions. So just to go over it quickly, we've got this is the problem of quantization that we have to solve. The Narasimhan Seshadri theorem converts into a problem in algebraic geometry. And then we have the good luck that because of effects that were actually already known, the problem in algebraic geometry we get has an already known link to the space of conformal blocks of the WZW model. So that's the basic link between 2 and 3 dimensions. It depends on the Narasimhan Seshadri theorem. We weren't in the good case of a coprime case where the original theorem applied. So we actually need, well, to do this purely in algebraic geometry, exactly the way I said, we need the stronger version by Seshadri where he included semi-stable bundles. Otherwise, we could try to work in differential geometry with L2 sections, but technically that would be harder. So it's at least illuminating to know the slightly stronger version of the theorem with semi-stable bundles. Actually, I explained this in the absence of knots. To incorporate knots, we need the later refinement by Seshadri to include parabolic structure. So remember, when I introduced the Jones polynomial, we started with representations of the braid group. So points were moving around in the plane, but we can stretch out the time dependence to be very slow and think of the local picture as being that the points are stationary. So a local picture looks like this with points at some positions in the plane and moving in, not moving in time. Now you can show that the phase space that has to be quantized is a moduli space M prime of flat bundles on a punctured surface with a prescribed conjugacy class of the monodromy around the p's, which depends on the representations. So these lines are supposed to represent representations. In gauge theory language, they are external charges in some representation of the gauge group. And then their propagation along the world line, you take the holonomy of the connection along the world line of the external charge. So the phase space that has to be quantized is exactly the moduli space of flat bundle with point singularities that was on the left-hand side of Seshadri's theorem. And the theorem identifies M prime with the moduli space of semi-stable homomorphic GC bundles over sigma with parabolic structures at the points pi. And again, that's the answer. That's an algebra geometric description of the space of conformal blocks for WZW conformal blocks with insertions of primary fields. There's a key ingredient missing in what I've said so far. We picked, to invoke the Narasimhan Seshadri theorem, we had to pick a complex structure J on sigma in order to quantize the moduli space of flat bundles with or without point singularities. Of course, the choice of complex structure violated topological invariance. So now we have to show that the Hilbert space Hj that we construct in complex structure J really does not depend on J. Now, as I explained on Thursday, such a statement would be generically untrue. So this is a special case where it is true. It's one of the 4 examples I gave where exceptionally different polarizations lead to the same equivalent quantizations. In this case, you construct a projectively flat connection over Teichmuller space that lets you compare the Hj's for different nearby J's. It's a very important part of the story. It involves adapting to infinite dimensions some simple facts about quantization in finite dimensions. And it's a rare case where issues we discussed on Thursday are important in quantum field theory. But it would take us rather far afield from Narasimhan and Seshadri, so I won't explain it today. It would take us into things that are important in geometric Langlands, but farther afield from Narasimhan and Seshadri. However, I do want to make contact with something I said Thursday. We don't have a good understanding of Chern-Simons theory with non-compact real semi-simple gauge groups such as SL-NR. And the reason is that the Narasimhan-Seshadri theorem doesn't apply to flat bundles with non-compact structure group. The closest thing that does apply is Hitchin's theorem about Higgs bundles. And after picking a complex structure J on sigma, we can indeed use that theorem, as Hitchin did, to construct a Kähler polarization of the appropriate phase space M. And we can quantize in that polarization. But we don't understand in what sense the resulting Hilbert space Hj is independent of J, so we don't know how to exhibit topological invariance, even as conjectures, let alone proving the theorem. So I've made a broad brush statement. There are important special cases in which you can say more, but what I've said is true generically. That means for generic groups and also for a generic topology of the bundle. Now, there's one much more recent contribution by Seshadri I want to mention, at least briefly. Seshadri and Balaji developed a theory of homomorphic bundles over a Riemann surface with parahoric structure, which is more general than parabolic structure. There's also a gauge theory approach by Balch, and there have been other more recent papers. I only learned about this paper in the last few weeks, and I don't yet understand enough to describe it in detail. But Balaji is talking today, so perhaps he will describe this work. I'll just make the following remark. A little over a decade ago, Gukov and I wrote 2 papers on surface operators in the context of gauge theory and geometric Langlands. So in the first paper, we used Seshadri's theory of parabolic structure, or more precisely, the extension of this to Higgs bundles by Simpson and later other authors, to describe in gauge theory the ramified case of geometric Langlands. Actually, this was the case of what's called tame ramification. So tame ramification involves parabolic bundles. And a piece of it is the way that the Seshadri theorem comes in. But after writing the first paper, we started worrying about more general types of singularities that we hadn't considered in the first paper. We tried to analyze these in the second paper, but we weren't able to get a systematic picture. This was actually a little bit before this work. And I didn't learn about this work until a few weeks ago, as I told you. Since learning about parahoric structure, I've been thinking that it might provide a better framework for at least a large part of what Gukov and I were trying to do. I don't know the answer about that yet, or whether it'll be all part or not, or just orthogonal, but it looks like parahoric structure probably is at least one of the ingredients we were missing. So to summarize what I've said today, I've described some of the celebrated contributions of Narasimhan and Seshadri, and I hope to have given you at least a few hints of the role they've played in theoretical physics. Thank you.
Well, thank you very much for this amazing historical and mathematical review. We do have a number of questions in the chat, and then we'll let people raise hands and ask their own questions. So Ashwin, did you want to start?
I'm
Yeah,
just going to ask
sure.
one question. What does it mean to say that the angulus function, what does it mean to say that, okay. I'll answer a question you didn't quite ask, and then I'll answer the question you did ask. So the question you didn't ask was, what does it mean to say that Morse theory is applicable to Yang-Mills theory? Morse, for a compact, well, for the simplest case, is a compact finite dimensional manifold with a Morse function that has isolated critical points. Then you consider the gradient flow equation of Morse theory. And in that case, you prove that every point flows toward a critical point. So you get a stratification of the whole space according to which critical point a given point flows to. So if there's a unique absolute minimum, then a dense open subset of points flow to the absolute minimum, but other strata are important. And then Morse had what are called inequalities for the Betti numbers of a manifold in terms of the critical points, and it's proved by considering this stratification. So a Morse function is called perfect if the Morse inequalities are saturated. In other words, if the Morse inequalities are actually equalities, which means that the critical points are as few as they could be given the Betti numbers and the Morse inequalities. The usual way to prove that is that if the index at a critical point is called the number. Take a Morse function at a critical point and look at its matrix of second derivatives. The number of negative eigenvalues is called the index. And if one has the form of what's called the strong Morse inequalities, you can see that if the critical points are all even, then the Morse function is automatically perfect. And for example, in Bott's famous work, in the original proof of the Bott periodicity theorem, he'd used the fact that certain Morse functions on loop spaces were perfect, except they were perfect in an equivariant sense. That means you have to generalize what I said slightly to allow for a symmetry group acting on the problem. So now going to Yang-Mills theory, saying that Morse theory applies to the Yang-Mills functional. So in order for it to be a perfect Morse function, saying that Morse theory applies means that if you look at gradient flow, which is now a parabolic PDE in 2+1 dimensions, you want the same idea of Morse to apply, that you get a stratification of the whole space of connections. You want to prove that under gradient descent, every connection flows to a critical point, a classical solution. So as I mentioned, roughly a decade after the Atiyah-Bott paper, it was proved that that was the case. Now, Atiyah and Bott were able to find all the classical solutions because that's actually elementary for Yang-Mills in 2 dimensions. And in the equivariant sense, the Morse indices were all even integers. And therefore, they knew that if Morse theory applies, the Yang-Mills function was going to be an equivariantly perfect Morse function. And technically, that led to a computation of the Betti numbers of the moduli space of flat unitary bundles that matched Harder and Narasimhan. Okay, that was Aswin. What are the parabolic weights in the WCW language is Jacques' question. So in the WCW language, you have a representation of the group, which has a highest weight. And you divide the highest weight by K. And what you get, actually, let me even say it differently. Okay. Okay. Then what you get is the parabolic weight. So it's the highest weight of the representation divided by K is the parabolic weight. So and that's going to be rational because the highest weight was integer and we divided by an integer K. So we would, if you think about it, as you let K vary, you can get all possible rational weights. In the Seshadri story with parabolic weights, the parabolic weights can be any real weights, and the rational ones come in for WCW. I think I'll stick with that answer, but if there's a follow-up question, we can say more. Does the Narasimhan-Seshadri theorem permit inclusion of torsion? Let's see, what do we mean by torsion? By torsion, we might mean, for example, if the gauge group is SO3, we can study bundles with different values of the second Stiefel-Whitney class. And in gauge theory, you could weight them by different factors. Perhaps that's what the question means. If that's what's intended, then yes, the Narasimhan-Seshadri theorem applies separately to each topological component of the space of bundles. I said that Balaji might talk about power hierarchy structure, but he did talk about it, Aswin points out. Okay. Well, I'll try to watch that later on YouTube. If it already happened, it was at a bad time for me here in Seattle, where my talk started at 8 a.m. So I'll see you later in Seattle. And if I'm lucky, maybe there was well, we'll see how, I hope to learn a little bit more.
So there's a question from Pranav Pandit.
Yes, go ahead.
Yeah, hi. So my question is motivated by a project I've been working on for many years with Haydn, Katsakov, and Kontsevich, where the goal is to sort of generalize the Donaldson-Uhlenbeck-Yau correspondence or the Narasimhan-Seshadri theorem, so that holomorphic vector bundles are replaced by objects in some triangulated category, which you think of as either some category of A branes or B branes.
Mm-hmm.
And the notion of stability is replaced by the Bridgeland stability,
Mm-hmm.
which is the sort of string theoretic analog, I guess, of
Yes.
stability here. And so I was just wondering, I mean, you briefly mentioned B-branes and thinking about Narasimhan-Seshadri in terms of B-branes in your talk. Could you elaborate a bit on that and maybe say how do string theorists think about this? And is there a conjecture, is there like a conjectural statement which would give a stringy analog of Narasimhan-Seshadri theorem with the Hermitian-Yang-Mills equation replaced by some deformed version of the Hermitian-Yang-Mills equation?
That's a great question. I'm afraid I don't have much to suggest. Perhaps the way I stated some things gave you too much hope about how much physicists understood, but not enough to be able to answer your question.
So have they considered cases where it's not just homomorphic vector bundles, but say complexes of vector bundles, and maybe in examples on higher dimensional spaces?
Well, in the application to the, after all, this stability condition you mentioned started with the work of Michael Douglas, who pointed out, I think I will only be telling you things you know though, and things you know much better than I do. He pointed out that in the application to the B model, yes, okay. First thing he pointed out was that in the B model, you should consider complexes of vector bundles. And the second thing was that a stability condition was important. I'm almost certain there's nothing in that area that you don't know much better than me, so I don't expect to be able to say anything useful.
Thanks.
Sure.
Ali?
I'll ask a question. Go ahead.
Hi. Thank you for the talk. I have two questions actually. So one question is about this relationship between the space of sections of the pre-quantum line bundle over moduli space of flat connections, and some abstract description of conformal blocks by Siegel. So you mentioned that physicists are not aware of it. I am a physics student. I'm not aware of it. Can you elaborate on it a little bit more, if possible?
Well, I'm torn between between giving you an abstract explanation and telling you what happens in GINA 0. So the abstract explanation is that the space of conformal blocks by definition is the space of solutions of the Ward identities. And it depends on exactly what one knows, but once it's suggested that it's true, it's not that hard to see that the space of solutions of the Ward identities is the same as the space of homomorphic sections, blah, blah. But I didn't plan to explain it, so my thoughts aren't well organized about how to explain it. If you have the right setup about what you're doing, it is kind of a tautology to prove it abstractly in general. I'm not sure. Let's discuss it concretely what it means in GINA 0, though. So first of all, what is the moduli space of parabolic bundles in GINA 0? First, let's discuss what's the moduli space of stable, of unitary flat bundles without singularities. That's easy because the fundamental group is trivial. So the moduli space is just a point. Now let's put in some singularities. But we'll think that K is extremely large. In other words, I'll make statements that are only true for generic K, but since K has to be an integer, the only way K can be generic is to be very large. It's not allowed to be the square root of 2. We want K to not have any exceptional value at which something else would happen. There will be finite, any sufficiently large K will do. So think of the impurity you put in. Let's suppose the group is SU2, where you might be more familiar. You can get a representation of SU2 by quantizing a two-sphere with a certain symplectic structure. So now we have many of these singularities. Okay, what is a point on the two-sphere? It picks a U1 subgroup of SU2, but in algebra geometric line, it's parabolic structure.
Right.
So what Seshadri's theorem means in the case of the two-sphere is that roughly you've got all those point singularities, which at each point you have a vector in the Lie algebra that tells you a point in the local S2. And well, let's proceed as physics. So you've got representations at impurities, and you have to take it, you want to impose Gauss's law, but at large K means weak coupling, and in the weak coupling limit, you just take the invariant subspace. Gauss's law will just tell you that in the tensor product of local Hilbert spaces, you take the invariant subspace. So that's the answer for the space of conformal blocks for a sufficiently large K in genus 0. Now, I'm worried that there are too many things I haven't told you in these lectures that you need to know, and I have no idea which of them I should assume is known. From an algebra geometric point of view, each of these two spheres was a CP1, and you could quantize the CP1 with its line bundle to get spin K or whatever.
Right.
But if you want to take the invariance, instead of quantizing and then taking invariance under the compact group, you would just take invariance under the complex group. So the tensor product, the product of all those CP1s divided by SL2C is what Seshadri called the modular space. That's what, I'm making a mess of this explanation, sorry. I think you accept the fact that to include an impurity, you would have a CP1 if the group is SU2. But
Yes.
a point of CP1 defines parabolic structure in Seshadri's language.
Okay.
They're the upper triangular subgroup of SL2C that leaves that point fixed. So the choice of a point in CP1 is a reduction from SL2C to a parabolic subgroup. So the many points with parabolic structure is Seshadri's moduli space of parabolic bundles, where I'm ignoring the stability condition in that statement. And then homomorphic section, to construct the moduli space, we divide by SL2C. Well, I zigzagged a lot and I left out a lot of holes, but I told you most of the ingredients of an intuitive explanation of what the statements mean in genus 0.
Right, and now the space of sections over this moduli space of this pre-quantum line bundle that should be identified with this invariant subspace of tensor product of the representations.
Well, there are two things well, if you want to just take invariance, they're invariance with respect to SL2C.
Okay.
There are two approaches. It has to do with whether you want to take invariance first and then quantize, or the other way around. So as an algebraic geometer, Seshadri would say, you take the invariant subspace under SL2C and take the homomorphic sections on the quotient. They're actually the same as the SL2C invariant homomorphic sections upstairs.
Okay.
A little bit closer to quantization, you'd say that the space of all sections is the Hilbert space before you impose any invariance. And it actually doesn't matter if you impose invariance after quantizing, that means after you take the sections. It doesn't matter if you impose invariance under SU2 or SL2C, because SL2C acts homomorphically, and the SU2 invariants are automatically SL2C invariants.
Okay.
Sorry. I can't do much about it right now.
Thank you it is. I think yeah, I got the basic idea.
Okay.
So I had one question, but I'll let other people go first, and then if my turn comes back, then I'll ask the next question.
Okay, fine. I guess Aswin then.
Hi, Edwin. So mine is a little imprecise. So given the connection between bungee and 2D Yang mills, one would have naively thought maybe one can find a explanation for what it means to have a Hecke modification purely in 2D Yang mills. But the best explanation I know is your explanation from Friday, which is to think of Tuft operators in 4D and then sort of go down to 2D.
Well,
do you have some intuition for why? Why does 4D starting point is somehow easier? Yeah.
Well, 3 is enough because I really only use 3 dimensions in that explanation. Not really. In 3-dimensional gauge theory, there are Tuft operators, which are local operators, point operators. And that gives a physical role for Hecke modifications in 3 dimensions. There isn't a clear physical role for Hecke modifications in 2 dimensions, even though they're operators that act on 2-dimensional gauge fields. Well, okay. I'm not sure. Okay, sorry, maybe I've given the wrong answer. So what are called spectral flow operators in 2-dimensional current algebra or Kac-Moody algebras are related to Hecke modifications. So that's a place where physicists doing purely 2-dimensional conformal theory, field theory, not Yang-Mills theory, do use Hecke operators. After all, that's close to what Balanson and Drinfeld did in geometric Langlands because they were using their Hecke operators for current algebra, Kac-Moody theory at the critical level. So maybe the best answer to give you is that maybe not for Yang-Mills theory, but yes, for conformal field theory in 2 dimensions, we do use Hecke operators. Oh, sorry, yeah, Hecke operators.
Okay, thanks.
I guess Ali and Pranav both have questions.
In which order?
You can go first.
Okay. Yeah, hi. So I actually have 2 questions, but maybe I'll ask one and leave the other one for next time if there isn't time. So you briefly mentioned this connection between parahorics and surface operators. Could you just say a few words about how that, what the idea is?
Well, in 4 dimensions, a surface operator in general is a codimension 2 singularity. And so parabolic structure is in a Riemann surface is a singularity at a point,
right,
which is codimension 2. Parahoric structure is a more general type of singularity at a point. What I haven't understood is exactly what kind of construction in differential geometry in gauge theory corresponds to parahoric structure. There are some papers, but I haven't really understood them yet.
I see. So that would be the sort of Hermitian-Yang-Mills side of this.
Yes, instead of, well, wherever, literally, as I said in my talk, parabolic structure is related to tame ramification. Well, not just in what we did, but in the mathematical theory. What people call the tame case of ramified geometric Langlands has to do with bundles with parabolic structure. I'm not 100% sure, but I expect that some of the more general singularities that Gukov and I didn't have a general understanding of are parahoric. Maybe all or almost all, maybe just some, I don't know.
Thanks.
Sure. Ali again, I guess. I can't hear you. You're muted, I think.
Right. Yes. Now I'm unmuted. So if I understand right, there's no just like there is a 2D interpretation of the space of the Hilbert space of SU2 Chern-Simons theory, for example, as a space of conformal blocks of 2D WZW model. is there a similar interpretation for SL2R turn assignments? And if not, then if it's not known, then is there anything that you generally expect, but it's not been shown yet?
I think it's an important question. There's nothing that's something, one would hope something is true, but it's not known what's true. There's no group other than SL2R, I don't think, where the conformal field theory has been studied in detail. And in SL2R, an analog of the statement that the space of conformal blocks for SU2 is the space of homomorphic sections over the moduli space isn't known. And I don't have any idea what to expect to be true. I think it would definitely be worth understanding it.
Okay. Okay. All right. Thank you.
Sure.
So last chance for more questions. Ali, are you still raising your hand?
I guess Pranav.
Pranav?
Yeah, so this is a quick one about your previous talk, I think, where you said that the stack bungee should be thought of from a physical point of view as working in 4 dimensions.
Well, adding 2 more dimensions is the way to say it. So,
sorry?
Working with the stack means that you consider 2 more dimensions. So what I said was that a category associated to a stack should come from 4 dimensions, with 2 for the category and 2 for the stack.
I see.
So that was why geometric Langlands should come from 4 dimensions.
And passing to the coarse moduli space is like going down to 2 dimensions?
Well, it's like making a 2-dimensional approximation. Yes, roughly.
I don't fully understand how that, what the dictionary is, but maybe there isn't enough time. I can ask you later.
Tomorrow would be better for that question, because we'll be on geometric Langlands again tomorrow.
Yeah, sure. Thanks.
Sure.
All right, so let's everybody thank Edward Witten again for the beautiful talk, and we'll continue tomorrow.
Okay, see you tomorrow at the same time. Bye.
Bye.